And I oftentimes get questions about my midterm grades. Kids come in and ask me. So I thought I'll just try to dispense of most of the questions here. Of course, you got a test back, most of you. Yeah, all of you, because I've got just two. The absent people are right here. So that got factored into your grade. To be honest, I did that. I graded this like 2 weeks ago. I think the grades were probably in Moodle on Saturday, maybe, or was it Friday? Anyway, it was really early because, I was traveling Saturday, so it wouldn't have been, I don't remember. But anyway, whatever the situation, it's been too long. I don't remember what you did right or wrong, but you do. You know what you did right or wrong because you can look at it. Please do feel free to come up afterwards and complain. I know that you're good at that. I had several people do that for exam 1 and beg for mercy, or maybe just for a point here or there, and I actually gave a few people a point here or there. So if you do have questions or concerns about your particular exam, please do see me afterwards, and we'll deal with it. Sorry about the title. It was not Test 2 practice problems, was it? It was the actual exam. I just used the same file that I used for the practice problems, and I didn't change that part of it. So I'll have to be more fastidious when it comes to the next exam. But none of you are confused. You all did it as if it was a real exam, not a practice. Well, I don't know. Maybe some of you thought it was a practice exam? Yeah, you can come talk to me about that if that's the case. Anyway, getting back to this. So kids will come and ask me, like, why did I get, on my midterm? And so here's one of the most common questions I get. I thought I'd answer them for you. Is I just got my midterm grade. Why is my grade so high? Oh, by the way, midterm grades, they're kind of an anachronism now, aren't they? Now that we have Moodle, you can see your grade, and every day you can get a new midterm grade, can't you? Although I was careful, I copied, I'll explain in just a minute what happened with the grades. So some of your grades plummeted this break for a reason that I'll explain in a minute. But anyway, I just got my midterm grade. Why is my grade so high? Some of you are surprised it's super high. Well, you probably completed all your homework. You can check your grade report on Moodle. Make sure that I have all the correct grades for your exams because, someone here like this person has a 27 on their exam. I might have recorded in there as a 72. I'm just kidding. They don't have a 27. But I can make a mistake. So if you have, the wrong grade in the grade book, let me know. I can fix it to get your grade back down to where it should be. Also look for perfect homework scores in the grade book. That wouldn't be my mistake. It would be your mistake for doing the homework. You can always lower your grade in the future by not completing your homework. That's a good way to do that. Also, don't bother to study for the exams. You can bomb an exam or two, and that'll certainly lower your grade. Now, of course, this is kind of a joke. In reality, the question that I sometimes get is this one. Why is my grade so low? However, you can probably just figure out what I'm going to have here. It's the opposite of what I just had for the graded too high, is you probably failed to complete some of the homework. Check your grade report on Moodle, and you'll see this. Now, quick note about the homework. I discovered that Lumen, so thank you for working with me on this Lumen thing as I get used to this new platform. However, one thing that was somewhat unexpected was if someone chose not to do a homework assignment, Lumen recorded it in my Moodle gradebook as a dash. That is like a blank, like when you don't do a quiz because you had to go have surgery or whatever it was. I give you, if you're an excused absence, I give you a blank. Well, the blanks for the homework shouldn't be blanks, they should be zeros. So over break, I went through and I changed all the homework blanks. I had to do it manually. It was kind of a pain, but I did it because I care. Anyway, I changed all those blanks to zeros. So if you're one of those people who chose not to do a bunch of your homework, all of a sudden your grade is probably a good deal lower now because now you've got a bunch of zeros. So check the grade book and see if you've got a bunch of zeros, that can be fixed. Don't worry, there is hope for the future. But for now, that might be why your grade is so low. Make sure that I have the correct grades for your exams. Just as I could have accidentally recorded a 27 as a 72, it could go the other way. I'm typing all these grades in. I had 100 grades to type in over break from exams, and I just sort of go, doop, doop, and I type it in. But something might happen between looking at the grade and typing it into the computer. And, mistakes happen. So I want to correct those mistakes if they have happened. Look for zeros under the homework. That's probably another reason why you have a low grade. By the way, a 0 in a homework, it snowballs. Because if you don't do the homework, then you're not going to do well on the quiz, and you're not going to do well on the exam. So it just really snowballs, and you want to stay on top of the homework from here on out. It's going to do, so you can complete your homework for a discount. You know how the system works. If something, oh yeah, so here's the deal though. Because of the way Lumen records the grades, I had to override all the blank grades as zeros for homework. So if you choose to go back and do some old homework, let me know so that I can override the grade. Because if you do some old homework, you might get, I don't know, whatever it is, a 50%, and it'll show up in the Moodle gradebook as a 0. So let me know if you do any old homework, and I will fix those grades. Yeah, even if you just get a 1 point for an assignment, it's better than a 0. Seriously. So if you're like, I don't know how to do this stuff, go in and compute some derivatives or something and do something, and you might get a little bit of credit. Also, I mean, I'll sit next to you and help you do the homework. I don't mind doing that. So make sure you take studying for the exam seriously. Use the study guide. Come visit me in my office at 6:30 in the morning if you need to. Also, study groups. Super helpful, so helpful to work in groups. Some of you have established your study groups already. You're doing great. Some of you need to find a study buddy or a study group. So please do make that a priority for the next exam especially. Okay, so that's that. And like I said, it's been so long, I have no memory of grading. I do remember grading this exam, only in the sense that I was thinking, if I get these done, I don't have to do them while I'm in North Carolina. So I just get them done. So that's another reason why I might have made mistakes. So if I did make any mistakes, please do let me know so I can correct them. That's that. Okay, so we're shifting gears. It's very exciting, at least for now. So for today, it's going to feel, let me be honest with you, second half of Calc 2. I don't know if you've heard horror stories about Calc 2. Calc 2 is the hardest of the calculi. Calculuses? Calculi. I'm going to go with calculi. Anyway, the hardest of all of them is Calc 2. And you might have thought, oh, it's because of all the stuff that we've been doing. Oh, it gets worse. Well, it doesn't get worse. It gets different. So all of a sudden, we shift gears, and we do things that are not at all like this. So the stuff we just did on our exam, you're going to say, where is this new stuff coming from? It's like coming out of left field. We have reasons for why we care about this stuff. And hopefully they'll become clear at the end. But for now, it's going to feel a little puzzling. So we shift gears. Things get a little bit weird for some time. Today, though, I feel is kind of a nice transition. Well, it's not really a transition. It's going to feel like we're just doing something completely new. So, and now for something completely different, sequences. So, sequences of numbers. Trust me, this has to do with calculus and limit. Well, you're going to see limits for sure today, but it does have to do with calculus. So, most of you are probably familiar with the Fibonacci sequence. If not, I'll show it to you. We're not going to be using this for calculus, but it's a nice sort of transit, because some of you are like, yeah, I know Fibonacci. Well, if you don't know Fibonacci, here's what the Fibonacci sequence is. It's this sequence of numbers. A sequence, by the way, is a bunch of numbers with commas between them. It's just a sequence of numbers. Here's the first one, here's the second. We keep walking down the road, and you get number after number after number. So that's the Fibonacci sequence. Oh, crud, this is not on my iPad, so I can't write on it. I'll switch to my iPad here in just a minute. Just a minute. How do I do this? Oh, here. Yeah, let me switch. Here, let me see. Can I get something else? Each term is the sum of the previous two terms. So go ahead, and if you know about the Fibonacci sequence, this will be easy. If not, I don't know, it's like the same numbers on the bottom and the top. Why did I do that? I don't know. But tell me what the next number is, and then the number after that. Just take a minute and do that while I freeze the screen and switch over to this here. So I like to write. Here we go. This is good. Okay, we're back. Let's see. Oh, sorry. Unfreeze. There, we're back. But now this is my iPad, not the computer. Okay, next two numbers. Oh yeah, let me pick a rando. So each number, just in case you're not seeing it, each number, so this 8, it's the sum of 5 and 3. This 13 here is the sum of 8 and 5. Okay, good. Now let me find this. So we want to know the next two numbers. So let me randomize here. Mariah, what's the next number in this list, do you think? 34. How did you get 34? Ah, very good. 13 plus 21. Okay, one more here. Cooper, what's the next number in this list? 55. How do you get 55? Excellent. 34 plus 21. Okay, so, oh, there it is. Sorry, it's confusing because I have, here, I'm just going to have to shut down the, yeah. Okay, that's better. Sorry, I had two things going that looked exactly the same on this screen. Okay, now we're good. By the way, you might say, what's the point of all this? Well, this is just for fun, but there is an actual use for the Fibonacci sequence that you might not be aware of, and that is that if you want to convert from miles to kilometers or kilometers to miles, because certainly America is going to join the rest of the world, hopefully, at some point, maybe in 200 years, and use metric, and you want to make this conversion from miles to kilometers or kilometers to miles, you can do it very easily using the Fibonacci sequence. Here's what I mean. Let's say that you're driving somewhere and you want to drive at 55 kilometers per hour. That's about the same, sorry, I should have made like this, as 34 miles per hour. So miles and kilometers, the conversion is right here. What is a 5K? A 5K is about 3 miles, isn't it? 5K, 3 miles? Isn't that cool? A 13 kilometers is the same as 8 miles, about. It's not exact, it's pretty close though. What about 55 miles? 55 miles, how many kilometers is that? 89 kilometers. I know, it's not exact. If you do it in Google, it's going to say 88.759 or whatever, but close enough. So you might say, well, I don't know if I want to find out, like sometimes you're interested in 100 kilometers. Or no, that's too easy. Let's say you're up in Canada and you're driving to Montreal and you see a sign that says Montreal, 75 kilometers away. 75 kilometers. So what is that in miles? Well, here's how you do it. 75 is the same as 55 plus, close enough, 21. So 55 is 34 and 21 is 13. Add them together and you get 47. So that's 76 kilometers. It's about 47 miles. Okay, enough of that. It's just kind of an interesting thing that you might not be aware of. I guess that if you took this to the extreme, you'd say, well, look back there. 1 kilometer is equal to 1 mile. Okay, don't do it back there. In fact, don't start it until here. Then it'll work pretty good. Okay, onward. So a sequence is thought of as a list of numbers. We have this list of numbers. It goes on forever and ever. And so we're going to name the list of numbers. We'll have the name be like A or B in this case. Maybe back here, it would be good to use F. So this would be F1, F2. Actually, Fibonacci always starts at 0. F0, F1, F2, F3, whatever. Anyway, so the Fibonacci numbers, you would use F. Here I've got A. The A, think of the A as being the name of the street or the name of the sequence, but I like to think of a street. So this is the street name, and these numbers here are the house numbers. So you have a street, the A street, and then house number 1, house number 2, house number 3, house number 4. These numbers down here are the actual people who live, well, numbers that live in these houses. So the 3 lives in house 1, the 5 lives in house 2, the 7, and so on and so forth. Those dots mean this goes on forever and ever. And for most sequences, at least the simple ones, for today, you're going to be able to look at this and say, oh, I know what this sequence is. In fact, let's see if we can figure this out. Let's find another volunteer. Luke, Do you know what comes next in this sequence of numbers? What did you say? 11, very good. So 11 is next. And then Joshua, what's after that? 13. How do you know it's 13? You're just going up by 2, aren't you? You're just adding 2 each time. Very nice. So this is you're just adding 2 each time, add 2 each time. Very nice. Okay, so that's the add 2 each time sequence. We have a name for these kind of sequences that we'll get in just a bit. Oh, look, I've got more stuff. I don't want to look at that, so I'm going to move it on. Okay, so this a sub n, hopefully what we want, our goal, at least for today, is to come up with a formula, an expression, a function that describes this a sub n. And basically the a sub n is a sequence, it's a function whose domain is the positive integers. This is all technical stuff. And we're going to write a sub n, oops, here, this does matter down here. So if you have these, here I'll do this here, a1 is equal to 3, a2 is equal to 5. This is the sequence from the previous slide. In fact, I suppose I could actually, oh, why? What? Sorry. I don't understand what I'm looking at here. Oh, I'm sorry. You know how after break you always have to sign back into everything? It's making me sign back into Microsoft. Let me see if it'll let me do it. Okay, there, I'm signed in. It's just, sorry, neither here nor there, doesn't matter. Okay, so this sequence back here on this previous slide, it wasn't going to show me the previous slide because I wasn't signed in for some reason. So that sequence, A1 is 3, A2 is 5, A3 is 7, A4 is 9, etc., etc., etc. So we're going to write the notation of these sequences in a bunch of different ways. So there's 3 main ways, though. First way is this way. You'll see 3, 5, 7, 9, ... just to mean this thing goes on forever, and that's in curly brackets. Another way is down here with these curly brackets where we just say, okay, it's going to be a sub n, or why am I writing this again? I don't need to write those again because you've got them printed there. Now, what we're really interested in, though, is a formula. Is a formula for this. Now, someone, was it Joshua said, it's just you're adding 2. It's the adding 2 sequence. But how can I express that in a formula? That's what I really want. And so what I'd really like is a formula. Now, I'll do this one for you, but there's a way that to do this for this kind of sequence. It's really not too bad. So this is going to be 1 plus 2 times n is my formula. Now you go ahead and double check that this is the case. So take my formula. I'll explain where that came from in a bit. Don't worry. But for now, just check it out. 1 plus 2 times n, when you plug in is 1, you get this. When in is 2, you get this. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 1 is 7. So you get that as well. And so here's how, the reason I wanted to write that down is because you'll sometimes see this. And the way that I interpret that is that I have a sequence where the formula is this, and those are the limits. So we're starting with n equals 1, and we're going forever with this sequence. So that and this mean the same thing. Not to worry, you're going to get to do some yourself in just a minute. Okay, so some sequences can be defined by giving the formula. So here's the notation for the formula. Here's the actual formula. And then if I wanted to write out the terms for this particular sequence, here's what they look like. So this is basically just another example of a sequence. So it's not really all that tough to do this. Let me do another one. Whoops. This one looks a little bit more complicated. And in calculus, we're going to be using sequences that look like both of those. In fact, this one is going to be even more common than that, just so you know. There's all sorts of weird sequences that we're going to work with. For now, I just want to, it's more like, let's plug these numbers in. So there's the notation. The formula looks like this. So it's not too bad. And then if you want to get the terms, so this one is more complicated. What you'd have to do is start with 1. Oh, this one doesn't have the limits, does it? Start with 1, plug 1 into that, and you get -1 times 2 over 3. So notice that because you have 1 plus 1 is 2. So that would be -2/3. Whoops, I keep moving things around. And then the next term, the next number in the sequence, plug n equals 2 into this. So here this negative, interesting thing happens. You get -1 squared is +1 times 3 over 9. So I've written that as 3/9 just to emphasize where it came from, but of course you could reduce that to 1/3. And then the next number is -4/27. The next one is +5 over 81. You can double check this. This is an interesting sequence because it goes from negative to positive to negative to positive to negative to positive. This is called an alternating sequence because it alternates between positive and negative. We'll be using that term later. For now, it's just a sequence, but it is kind of interesting. Okay, so we have a few more. So just to see, notice that this sequence starts out at n equals 3. And the reason why it starts at n equals 3 is because if you plug n equals 2 or 1 into this, you get a negative number under that radical, and that's illegal. So it starts with n equals 3, which is fine. Let's see what the formula is. It's just that, but notice that I'm specifying that n is greater than or equal to 3. And then when I write out the terms, they look like this. So you start off with when n equals 3, you get 0. When n equals 4, this is 1. When n equals 5, that's the square root of 5 minus 3, which is square root of 2. And so on. So that sequence is pretty easy. Don't worry, we have some for you. I'm looking right here at them for you to do. Oh, this one is fun. That one looks really scary, doesn't it? But check it out. This one is actually really an interesting sequence. Because if you do this, you know that the cosine cycles. It cycles around. And so what you end up with is, and I don't have the whole thing here, but you get 1 radical 3/2. That's the cosine of 1, this is the cosine. Oh, another thing, this starts at n equals 0. So most of our sequences will start at n equals 1, but every now and then you'll get a sequence that starts somewhere else. So this one starts with n equals 0. Cosine of 0 is 1. Cosine of pi over 6 is radical 3 over 2. Cosine of 2 pi over 6 is 1/2. The cosine of 3 pi over 6, which is pi over 2, is 0. And then this repeats itself. You get negative 1/2, negative radical 3 over 2, negative 1, and then negative radical 3 over 2, negative 1/2, 0. So it just cycles over and over again. So this is kind of like an alternating sequence, but it isn't quite alternating, but it does cycle. It does repeat itself. So it's kind of interesting. Okay, so let's see. How about this? Do the first 5 terms of that sequence. So take a minute, jot those down, and I'll find a volunteer here. All right, let's see how we're doing. Claire, were you able to write down the first 5 terms? Did I give you enough time? Well, you can just tell me what you got.
Well, I got, this starts at 1.
Yep.
Okay. So then, maybe 2 over 2, so 1.
Okay, 2 over 2, very
And
good.
then 3 fifths.
Okay, 2, 2, 3 fifths.
And then, 4 ninths.
All right, 4 ninths. Oh, wait, 4. When n equals 3, 4 eighths, isn't it?
Sorry, 4 eighths.
Yeah. But yeah, so here's at least these are the calculations you're doing, right?
Yeah.
So very good. So we're just doing these calculations to get these terms, and it's exactly oh, I've got them reduced. So yeah, 5/11ths would be the next one because it's 4 plus 1 over 12 minus 1, and then this is actually 6/14ths, which is 5 plus 1 over 15 minus 1, which you can reduce to 3/7. But very nice. So this isn't too bad. So doing this, easy, right? Plug and chug. So that's not going to be a problem. But of course, that's not, we don't just leave it with this. We always make things difficult in math. And so I want to do the opposite. So going this direction, that is taking a formula and turning it into a sequence, that's pretty easy. But what I'm really interested in is this, is going the other direction, starting with the sequence and coming up with the formula. Now, I should say that technically, I don't give you enough information here to answer the question of what the formula is. But I'll just tell you right now that the sequences, they continue in the most obvious ways. So like here, I'll give you this one. This one you're adding 5, then you add 5, add 5. So this will continue to add 5 each time. So the next one will be 22, and the next one will be whatever that is, 27, and so forth. So each of the sequences continue in the most obvious way. And the reason I have to say this is because each of these sequences, there's an infinite number of ways that you could continue these sequences that are non-obvious. So we'll stick with the most obvious ones. So take a minute, see if you can come up with a formula for any of these. If you can't get one of them, skip to the next. In each case, we're going to assume that the sequence begins with 1. So this is A1 right here. This is A2, and this is A3, etc., etc. Hey, let's see how we're doing. I'm curious to see if any of you have figured out any of these. Any of them is fine. So Max, do you have a formula for any of these four?
Yes.
What do you got?
I've got 5n plus 2 for the first one.
Oh, interesting. Okay, so let me just say something about that. That's not quite what I have. It's different. So what Max has is the same sequence, but if you begin at a sub 0. So notice that if you plug 1 into that, you get 7. If you plug 2 into that, you get 12. If you plug 0 into that, you get 2. So he's got the same sequence, it's just he started at a different place. Oh, you can fix it?
Yeah, it's 5n minus 3.
Yeah, 5n minus 3 is the one that I was thinking of here. But yeah, so this one and the second one are special sequences. 5n minus 3. I'll explain how to get, there's an easy way to find a formula for both of these, because they both have the same sort of format. But you don't have to do the second one if you're next on the list here, Ethan. Ethan, do you have any of these other ones that you'd like to tell me about?
Do the second.
Okay, what is the second one?
I have negative 1 plus 3n.
Okay, very nice, 3n. Now, both of these sequences have the same sort of general form in the sense that what you're doing is you're adding the same number each time. Notice here you're adding 3 each time, 3, adding. And here you're adding 5 each time. That should give you a clue as to where these formulas came from. In fact, every sequence that's like this will always have whatever the common difference, that's what this thing is called, this, you're adding the same number each time. Take that common difference, in this case it's 3, in this case it's 5, and attach it to n. So 5n for this one, 3n for this one. As far as the other number goes, you just have to figure out what you have to do to get the first term. Now, if this begins at 0, then it's easy. You just 5 times 0 plus that number, I guess, would be what you get. But since we're starting with 1, it's a little bit more complicated, but not terrible. You just have to say to yourself, if I plug 1 into this, 5 times 1, what do I have to add or subtract from that to get my starting number? And in this case, it's minus 3. Down here, it's minus 1 to get that first number. Beautiful. We'll have a chance to do that again. The next two are not this type. By the way, this type of sequence, we have a name for this type of sequence. This is called and let me write it, arithmetic. Now, I know that you look at that word and you think arithmetic, but the way it's pronounced in this context is arithmetic, with the emphasis on the E for medic. But so it's an arithmetic sequence, but if you want to think of it as an arithmetic sequence, that's fine. It's the most easy, the most basic of sequences. You're adding the same number, like using arithmetic. You're saying, oh, add 3, add 3, add 3. You're adding the same number each time. It's different from this next one. This next one, you're not adding the same number each time, and certainly not with the last one. But Eli, do you have any ideas for these next two, either of them?
The last one is negative 1 over 1 plus 1 squared.
Like that? Ooh. Okay. Times n. Ooh, you did it. Very nice. Okay, yeah, so it's complicated, isn't it? So notice that this thing has negative, then positive, then negative, then positive. So it alternates. And so that's where this negative 1 to the n comes from. And then the n is just the top number, isn't it? That's 1, 2, 3, 4. And then the bottom number, Eli recognized those are all perfect squares, but they're the perfect squares of the next integer. So for the first fraction, you have the perfect square of 2. The second fraction, it's the perfect square of 3. So you just add 1 and then square it. Very nice work there. Okay, this last one, I don't have a special name for that last one, by the way. But this next one I do have a special name for. Madison, do you have any ideas for this next one? This last one, the last one that we have to do? Maybe you could describe what's happening for each of these, like to get from one to the next. Like, do you know what the next number is in the sequence? Yeah, 1/32. And where did that 1/32 come from? It's half of the previous number. So you take 1/2 to start with, and then you multiply that by 1/2 and you get 1/4. Multiply that by 1/2 and you get 1/8. Multiply that by 1/2 and you get 1/16. Anytime you're doing that, anytime you're repeatedly multiplying by the same number, we have a special name for that type of sequence, but I'm just going to write down the formula for you here. It's just going to be 1/2 to the n. And there's no adjustment that needs to be made at this point. That's all it is, this particular sequence. We'll have to fix some of these. Why does this class go so quickly? In a bit. This sequence, by the way, is called geometric. Here, I'll write it down. This is a geometric sequence. And geometric means you're multiplying by the same thing each time. And every geometric sequence is going to have a sort of similar form to it. And they'll all look something like this, the form of the answer for your formula. Okay, so, oh yeah, there's nice. I've got the things in red there. These are harder. Why not? Let's give it a go. Yeah, give these two a go. Remember that we're starting with a sub 1. The first number here is a sub 1. And I want to know the formula. A sub n equals what? A sub n equals what? There's a very important reason, by the way, that we're doing this. And this is sort of to me, this is just like fun, like puzzles. But there is a reason. So if you don't like these fun puzzles, just hang on, because we'll be using these puzzles to solve actual calculus problems. Let's see how we're doing with these. I know it's a little bit more complicated, but once you start getting the sense of how this works, it's you start seeing the same patterns. So Rachel J., what do you say this first one? Do you have any ideas as to how you might write this, or maybe we can get started on it? Very nice, 5 to the n, because you see the 5 and then 25, 125, that's like a geometric sequence. So this will be 5 to the first, 5 to the second, 5 to the third. Very nice. Okay, next we need to deal with the top there. Matthew, do you have any ideas on what the top is going to look like? Very nice, n plus 2. So, oops, I put a 1 there. It's n plus 2 because you have 3. And that's 1 plus 2. This is 2 plus 2. This is 3 plus 2. There's one last thing we have to deal with, and that's the negative positive business, that alternating. I know, Matthew, you were probably about to say what you needed to do, or were you? Okay, I didn't know if you were going to, I kind of cut you off there. So we need to deal with this. Notice the first thing's positive, then the second one's negative, then positive, negative. So does anyone want to volunteer for real on how to deal with that? Any ideas? What do you think? Sorry, Sawyer.
negative 1 to the n plus 1 power.
Ooh, very nice. Negative 1 to the n plus 1. And so notice that here, if you just did negative 1 to the n, this first one would be negative, the second one would be positive. So we have to do a negative 1 to the n plus 1 so that this will be negative 1 to the 2, which makes this a positive number. Negative 1 to the third, that's a negative number. Negative 1 to the fourth, positive. Negative 1 to the fifth, which is 4 plus 1, negative, and so on. Beautiful. There's other ways to do this. You could do negative 1 to the n minus 1. It would result in the same thing. All right, see how you do with this one. So much fun that we can have, and we only have 11 minutes or so, 13 minutes? 13 minutes. I know I'm not giving you much time, but Rachel P., what do you think of this one? Any ideas? So when you notice that, is there any pattern that you see that we can exploit, maybe? Okay, very good. So the bottom gets multiplied by 3. So the bottom is multiplied by 3. What about the top? What's the top being multiplied by? Yeah, by 2. Yeah, I know. You've got the problem with this one is these two numbers, right? Because they're not fractions. They've been reduced. If I'd written those as fractions, you'd be like, oh yeah, it's super easy. But let's see if we can sort this out, though. The top is being multiplied by 2. The bottom's, that's the same as multiplying the whole thing by 2/3, right? So let's see, is that correct? If I multiply 8/3 by 2/3, I do get 16/9. And if I do 16/9 times, let's ignore the negative thing for now, the positive negative. Look at this, I do get, so look at this, Rachel figured it out without even knowing that she was figuring it out. So, you can always figure these things out. Now let's go back here and see if this still works. Let's say you start with 4 and multiply 4 by 2/3. Well, 4 times 2/3 is 8/3. Well, let's go back one more step. Start with -6, multiply that by 2/3, times, that's supposed to be a times symbol, times 2/3. Sorry about the mess there. Multiply that by 2/3. Look, 2/3 times 6 is 4. Look, Rachel's cracked the code. We got it. Okay, so we're multiplying by 2/3 each time. Here's the thing with multiplying by the same thing each time. This is going to be a geometric sequence. So geometric. So the way that you, once you've cracked the code and you figure out that you're multiplying by that each time, take that thing, raise it to the n power. Now we aren't quite done because we have to reconcile that with that. So the first number, ignore the negative for now, we'll deal with the negative in a minute. The first number has to be 6, but if I plug 1 into this, I get just 2/3. So I need to correct that. To correct it, I'm going to put a 9 here. Will that do it? And you might say, how did you know? Well, I did a little bit of basic algebra. 2/3 times something equals 6. The something has to be 9, doesn't it? So yeah, just do a little bit of algebra. So there it is. The last thing I'm going to do is I'm going to figure out this negative positive business. And so I'm going to need to do sort of like what we did up here, multiply by -1. This time I just multiply by -1 to the n because I'm starting with a negative and then going positive. By the way, you can combine all this like this. Notice that since this is to the n power and that's to the n power, we can put them together. Okay, here we got to do a super quick thing. I remembered this from, so this is from a different class, but I thought this was cute. Whoops, why is this not doing this? There we go, there it is. Yeah, there it is. Okay, so here's a bunch of sequences. Most of these are pretty simple. This is for another class that's like a basic class. It's this last one that I wanted to tell you about. This one, what are we doing here? multiply by 2, multiply by 3, multiply by 4. I don't know. That one's funky. This one's weird. This one, you're doing something weird. This one's easy. You're subtracting 5 each time, so that one's an arithmetic sequence. This one, though, has a story behind it. I was teaching in Philadelphia. This is like 35 years ago. A student came up to me after class and said, "I got the sequence for you." She wrote this down. And she said, "What number?" Or no, she said, "What goes there?" And I didn't know. I begged her for the answer. Class ended, like the end of the semester, and she never told me. It wasn't until I moved. I moved from far northwest Philly to the west side, the City Line Ave, and I started riding public transit. And one day I was looking up at the Green Line, the subway stations, and that subway, the Green Line, stops at 2nd Street, 5th Street, 8th Street, 11th, 13th, 15th. That's Milbourne Street. So that's the only one that's not a number on the Green Line. So I just like that. That was kind of funny. So we have that. One other thing, another interesting thing is this, and then we've got to take a look at the homework because I'm not sure. I don't think I got as far as I was planning. This is kind of fun. Online Encyclopedia of Integer Sequences, founded in 1964. Not online then, though. It used to be a book. Back when I was in grad school, this was changing from a book to being online. It's such a beautiful thing that you can use. For example, if you put in any sequence of numbers, 1, 2, 4, 8, 16, let's say, and let's see, what is that? Well, that happens to be the powers of 2. But it's also, what does it say? How many? It's 925 results. These are all have citations and stuff and describes it. And, okay, that's the first one, the most popular one. Going further, come on. How long is this? It's incredibly long. Why is it? Oh, there it is. There's the second one. The coefficients of the expansion of this. And you might say, well, those are just powers of 2. Well, they are up to a point, and then they stop being powers of 2. So that's kind of interesting that you have something similar there. So that is fun. You can also search for names. So if you search for not my name, you'll find sequences that have references to papers I wrote. So there's that. Let's take a peek at the homework, because that's what I'm concerned about. Here we are. We pull this over, and we'll take a peek at the homework. Look at this. We still have 5 minutes. We can do it. Okay, so you can see that here I'm just looking for a formula. I think all of these we're assuming that we're starting at 1, I believe. Let me just double check. Let's do this one for fun. Notice that this is 9/2, 9/4. You're multiplying by 1/2 each time. So the formula is going to be something times 1/2 to the n. So if this is 1/2 to the first, I guess it's 9 times 1/2 to the n. Let's see if I'm right. And yeah, I'm right. 9. It'll be okay if you do 9 times 1/2 to the n. So you'll have some like this. Oh, this will be easy. Finding the terms. Oh, limits. We didn't talk about limits. Okay, just a brief note about limits. It's the same as with calculus. If you do the limit as n approaches infinity of this, you can do this one in your head, can't you? You know, leading coefficients, 5/2. Yeah, that one's easy. Some of them won't be as easy, like this one. You'll have to think about it a little bit harder, but don't fret. We can always pick up the pieces tomorrow. And then, let's see, this sequence is, what is this? Unbounded or bounded? Okay, oh wow, there's a bunch of stuff we didn't get to. Do your best, you can read the book. Yeah, bounded just means that it doesn't grow without bound. Yeah, some of this will be pretty easy. Let's see how well you do without having the full. You can read the book and also look at the videos here, because there's some videos here. And you can always message me. Yeah, send me a message. I'll do my best. I got to get back into the habit of looking. All right, stick around if you want to complain about your exams. I'm going to turn off the videos so that no one can hear you complain. So give me a sec. Stop video recording. Stop.